have all these tests under our belt, which one do we use? That's the question. So my strategy for testing series is what I'm going to teach you now. Other people might do things in a different order, in a different way. It really doesn't matter that much. I've also uploaded a like a cheat sheet for you, which another student found. It's very extensive. It's got everything on that sheet. So that's helpful, but also might be a little bit overwhelming. So I'm going to simplify it as much as possible for what we need for this week. That sheet also has the stuff about the geometric series, telescoping series that we talked about, and stuff about power series and Taylor series that we're going to talk about next week. So that's at the end of everything. That's a nice sheet to have, but don't feel weirded out if you don't know what everything is or if you don't remember or whatever. So, and just because I'm not talking about it right now doesn't mean we won't need it later, but not likely that you'll need it for this week's work. Okay, so I just see some random series. What do I do? Well, the first thing I always do is test for divergence. Okay? Especially because you can look at that really quickly and sort of do it mentally. You don't necessarily have to write it out unless you're then if that's what happens if the series goes to 1 or 2 or whatever. Then you know, I diverges by the test for divergence. Okay? And then you have to write it out. But you can kind of look at it and gauge it first. Like, oh no, that's going to go to 0. I know I'm okay. Okay, then once I've done that, I want to classify according to type. Oops. Now what we saw is that certain things we just knew which test to use. For example, if it's a rational function, also possibly square roots, whatever, but rational or algebraic function, we're going to use the comparison tests. So limit comparison or regular comparison with an appropriate PC. Okay? So that's one thing. If I see factorials involved, I immediately use the ratio test. If I see powers, something, a function to 1 over n, or sorry, I'm sorry, a function to n, I'm going to use the root test. If I see an alternating series, I'm going to immediately use the alternating series test. If I see that it's something that's none of these things, but hey, maybe I can integrate it, and try the integral test. Now I might have to think about if it's something different. I might have to think about looking at the, for example, if it has like a sign n or something like that. Remember we saw those. Take the absolute values, absolute convergence, that kind of thing. All right, but for the most part, most of what we have fits into here. Okay. Sometimes you may have several options. You could do ratio test or root test. You could integrate it instead of doing limit comparison. That's all of those are, I'll try to point out some examples where you have choices. But basically this is my strategy. I'm going to try one of these things. It doesn't work for some reason. I'm going to go back and try something else. Okay? So that's the general idea. There's one other type that I wanted to, nah, not really. Okay. So that is that. So what I'm going to do for the rest of this lecture is I'm just going to throw a bunch of series on the board, and we're going to say which test I'm going to use to do it. I'm not actually going to do the test, but I'm going to actually tell you what the series does, but I'm just going to look at it and say, this is what I would try. Okay, straightforward. This looks like something that's a function to n, right? I've got n power in the bottom, n power in the top. I can even write it if I want, like that. So, root test. No. Okay, rational function. I'm just going to go directly with limit comparison here. And limit comparison is going to be, okay, n over n to the fourth. So I'm going to limit compare it to 1 over n cubed. Got this guy. All right, I see factorials. I'm just going to go ratio test here. Let me remind you guys real quick, because when we got all these tests going on, it's sometimes you forget what goes to what. So for ratio test and root test, that's the one where if you get your limit equal 1, then it doesn't help you. It's not as inconclusive. Whereas limit comparison, if you get your limit equal to 0 or infinity, it's inconclusive. 1 is perfectly fine with limit comparison. 0 and infinity are perfectly fine with ratio and root test. So just to go make sure and go back and kind of keep that in mind. And in fact, if you look at that cheat sheet, I think that it sort of has that in there. It tells you what. One, sine 2, sine 3, it's crap, right? That is not going anywhere. So this for sure diverges by the test for divergence. If I take the limit of sine n as n goes to infinity, obviously it is not 0 because the limit doesn't exist. Done. So that's n equals 2. Alternating series, I'm going to try the alternating series test. Okay, let me remind you guys, I maybe have mentioned this in passing, but it is confusing. The alternating, most of the tests will tell you if a series converges or diverges, right? There are some that are a little bit different, right? Test for divergence will tell you that it diverges, but if it fails that, it doesn't mean it converges. Kind of AST is sort of similar because alternating series test will tell you if the series converges. And if it fails the alternating series test, it doesn't imply that it diverges. Usually it does, though. And the reason, what you'll find out is if you look back at the alternating series examples from the homework, where it typically was failing was that the limit didn't go to 0. So if that Bn doesn't go to 0, then your whole An doesn't exist anyway, right? That is going to fail it's going to fail the AST, and it's going to diverge by the test for divergence. So that's typically what happens, and that's pretty much what you guys will see. A person has to do a little bit of work to construct a series where it fails the alternating series test, but it still converges. Okay? Yeah, I guess we did see something like that, but we'll talk about that later. Yeah. Just reminding you about that with the alternating series test. So let's see a couple others. What do I have here? This guy. Okay, it's got a square root in it. It's algebraic function, but again, this is more or less going to be great for limit comparison. And what would I limit compare it to? Square root of n squared over n cubed. So n over n cubed, or 1 over n squared, is what I would compare that guy to. What else we have? Oh, there's a couple more here. What am I going to do? Here. Well, that kind of looks crappy, but in fact, if I look at it for a few minutes, I can see that this will integrate pretty well, right? Because if u is 1 over x, then du is going to be minus n over x squared. So this is just due to u, more or less. So this is a great one for the integral test. It's even easy. And I think that by this point, like most of the series, we don't use the integral test, so it's easy to sort of forget about it. But don't forget about the integral test, because when you can use it, you can go pretty well with it. All right, this has a factorial, but it also has a power to the n. So, I mean, I guess you could do this with the ratio test, but it would be a lot easier if you did this with the root test. So I would definitely start with the root test, because you can write this thing n factorial over n to the 4th all to the n. So definitely root test. And this guy diverges to hell, so whatever. You can tell. I take the limit of that, I'm going to get n factorial goes to infinity so fast. Okay, anyhow. So let's look at something else. All right, here's an interesting case. So now we have a problem because it's a series of positive and negative terms, but it's not an alternating series, so this is a little bit different than anything I had on the board. So sometimes you will see something like that's like this, but then remember the business about absolute convergence, right? Let's check out the absolute value of an. If I do the absolute value of an, I got sine 2n over this guy, right? So that's like that, okay? But this is less than 1 over 2 to the n, which converges, right? Because it's a geometric series with r equals 1/2. So we can use direct convergence to show that this guy converges absolutely. So don't forget that little trick. Really, when you have something weird like that, this is a good time for that little trick. Now, the other thing I wanted to mention, sometimes you will see something, like remember, we did those, like something like this, okay? Again, that isn't really strictly, I didn't have that on my little board, but something like that, you would probably be easier to do something like that with the limit comparison or limit comparison, rather than, well, except I have the -5. Actually, I wanted it, I didn't want it that high. I wanted the minus to be in there, okay, when I did it, so sorry about that, I wrote that the wrong way. Otherwise I'll have a whole bunch of negative terms, that's not good, right? So anyway, that's what I was looking for, is something like that. You have to do a little bit of work with that, maybe look at a couple of things, but in the end, you want to kind of do that in terms of limit comparison. But now with the minus, it makes it more unpleasant. So that would be a couple of steps. I wouldn't give you guys one like that with the minus. If I want what I would be likely to give you, something like that. Okay, that's much more doable, right? Much more doable. You can do that with limit comparison with 1 over 5 to the n. So something like this, limit comparison. So you don't necessarily have to do limit comparison only with the rational functions. Sometimes it's useful with these geometric ones where it doesn't easily fit into the root test, right? Because if I take the nth root of this, that bottom is going to be a bit of a mess. So maybe I don't want to do that. I make my life a little bit easier with the limit comparison.